So I'm going to apologize first. I was asked to give a talk about CubeSats and CubeSat data availability, and what I ended up with is an incomplete guide to CubeSats related to GEM. And it's got sort of a radiation belt focus, but that's partly because of my biases, so I apologize to people if there's missions that I've left out. And the other part of that is CubeSat data is scattered, and I think that's kind of one of the shortcomings of it right now. There's no great clearinghouse for CubeSat data, and because these tend to be short missions, it's one of the things that would improve, I think, our ability to use CubeSat data is more people using data clearinghouses for their data. So I won't talk too much about what CubeSats are. I think most people know by now. I'll just jump right into a couple different missions and where you can get their data and what their data looks like. Some of the challenges that have happened thus far. So the first mission is CSSWE, the Colorado Student Space Weather Experiment. It was in a moderate inclination orbit. You don't get to pick your orbit usually as a CubeSat, so you take whatever free ride you can get within some bounding box that you've provided. And CSSWE was aiming to measure energetic particles in the near-Earth space environment. CubeSat there, I often refer to them as loaves of bread, but in this case, compared to the size of a football. The CSSWE student had a lot of student involvement. I think most CubeSats have thus far. You can see some baby-faced versions of people who are in this community still here. Here is the Reptile instrument, which was an adapted version of REPT from Van Allen probes. A lot of CubeSats have borrowed instruments or copied instruments. I think that's one of the sort of budgetary savings. CSSWE has been remarkably successful. 23 papers, upcoming 5 PhD theses, a couple really fantastic results there. CSSWE has also done a good job in my mind because they have put their data on CedoWeb. So this is a publicly available archive. There is a button for CubeSats. CSSWE is the only CubeSat there. So good for them. And I think more of us should take advantage of that. The available dates are here, 2012 September through 2014 August, with some data gaps. So CedoWeb will let you pull up this sort of data availability chart. You can see they had some system anomalies, I guess, that shut them down for a little while, but still a remarkably successful mission. They provide 6-second flux for electrons and protons in 3 energy channels for each. This is often how you see their data, but you can process it down to the 6-second level as well. The next mission I'm going to talk about briefly is Firebird. Firebird is collaboration between Aerospace Corporation, Montana State University, and University of New Hampshire. Firebird 1, I should say, which consisted of 2 spacecraft, launched in December 2013. It had power system anomalies. It didn't work very well. They got very limited data. And they respun the flight spares with a new power system for launch January 2015. And it's on orbit now for 53 months. It's still working really well. Although my grad students complain about it all the time. I think it's working very well. Firebird, similar thing. It's looking at precipitating electrons from low Earth orbit. A different approach to the data availability problem. So Firebird provides time resolution as good as 12.5 milliseconds and as many as 6 energy channels for the electrons. The CubeSats were magnetically aligned, but that's doesn't work quite as well as was originally hoped. And of course, magnetically aligned in the northern hemisphere is very different than magnetically aligned in the southern hemisphere for our detector. So be cautious with using the look direction as the magnetic field. Firebird generates as much as 960 times the CSSWE data rate, and that's a lot of data for a CubeSat. So how do you get that down? The answer is you don't. We operate with a scientist in the loop. That's one of the ways we operate. We downlink a 6-second resolution energy, 2 energy channels for an entire campaign. A campaign is about 3 weeks long. And then based on that, based on the scientist in the loop, we download the high-res, up the top here you see the context data, low energy channel, high energy channel not responding down here in blue, and this is what the high-res data looks like. So in total, we downlink less than 1% of the collected high-res. So it's a very limited data product based on what the scientist in the loop has chosen. This is what a campaign ends up looking like. This is actually sort of similar to what the CSSWE data product looks like. I've separated out here into northern hemisphere on the top 2 panels, southern hemisphere on the bottom 2 panels, and low energy channel on the top of each section and high energy channel in the second panel of each hemisphere. And you can see sort of the gross structure of precipitating electrons from low Earth orbit. But that's just one campaign. Because we are doing this sort of burst scientist in the loop link, this is what our context data looks like over the course of about 4 years. You can see very long data gaps while we are choosing these high resolution time periods to download. So if you want to use Firebird data, you need to first find out if we were in a campaign, and then find out if we happened to download the high resolution data that you were interested in. So the scientists in the loop, because it's such a narrow pipe of downloading data, they have a lot of responsibility, and it's not the easiest archive to work your way through. Especially after the first campaign, one of the things that we've been focusing on is to try and make a niche measurement in conjunction with other assets, because we have sort of this very limited data product. We look for conjunctions with Van Allen probes, other CubeSats, ARASE, RBSP, POSE, as well as balloon missions, which actually is one of the reasons why there are several of these long data gaps, is they were done in conjunction with the Barrow balloons, so we spent a while downloading a fair amount of the high resolution data from that time period. The data is available at Montana State. We update it daily. You can get it from a couple other locations, but I think this is the most current at all times. There are a couple caveats. There's some onboard clock drift that we can correct down to the sort of 1 to 2 second range. And if you want to do better than that, we have to look at the data pretty carefully, sort of in a case-by-case basis. And as I said, the attitude is not really well controlled by this magnetic alignment scheme, so be careful you don't know exactly where you're looking. Firebird was launched as a pair of CubeSats because they wanted to look at these small structures in microbursts, but it's just passively separating. So over the course of 14 months here, it was up to about 2,500 kilometers in track separation. That's way larger than the approximate microburst scale that's shown down here. And so really, beyond the first campaign, we weren't able to look at these small structures, but they're still operating 53 months later, and we can do a lot more with them. Passive separation adds up quickly. This is now 4 years on a log scale, and you can see, again, we got out of the microburst scale size very, very quickly. So, so we're looking now at much longer time separations, or equivalently much longer spatial separations. Shown here in blue is a different scheme. It's the AC-6 satellites, which don't use passive separation, or didn't use passive separation. And they were able to control their separation with, by using differential drag. AC6 was AeroCube 6. It's two 0.5 U, so remarkably small satellites, each 5 by 10 by 10 centimeters. Launched in 2014 in basically a sun-synchronous orbit, so they have somewhat limited local time coverage. Firebird has processed around. It was not quite as sun-sync, so Firebird has better local time coverage. AC6B operated through June of 2017. AC6A still has some limited functionality. The measurement here is 3 dosimeters. They're a little different on the two spacecraft. Both of them called dose 1 respond to 30 keV electrons and 235 keV protons. Dose 2, higher energy electrons, higher energy protons. And then dose 3 was split to a different response between the two spacecraft with 1 MeV electrons on AC6A and 20 MeV protons on AC6B. The data product was 1 second survey mode for most things, and then a 10 Hertz data project in what the team had identified as regions of science interest. Those were mostly radiation belt foot points and latitudes to the east of Africa at sort of most latitudes. Then there they would take a 10 Hertz data that looks a lot like what you see here at the top. And one of the nice things they saw was coincident microbursts across different scale sizes, as well as persistent precipitation structures that they identified as curtains. AC6 has some data caveats. They have a nice README file that I'll point to in a second. They get some cross-link noise when they're talking to each other, and they get some downlink noise when they're talking to the ground over North America. They do have a data quality flag. Over here I show their local time distribution when they were making simultaneous observations, so you can see there's a little bit of a sun-sync bias to a particular local time. And again, this is their spatial separation. So they were down to as little as 2 kilometers at time separation, so they really did a good job of looking at these small structures. The data is available on the Van Allen Probe's gateway. It's got a few contacts listed here, and they have a nice README file, as I said, on the gateway. It'll explain to you how to use their data and all the data caveats. And I believe some other AeroCube data is forthcoming, but I didn't have any details on that. Another mission, also radiation belt related, that is in operation right now is Elfin Star. This is a pair of 3U CubeSats from UCLA. Vasilis Angelopoulos was the PI. This was joint from NSF and NASA. The primary science instrument here is energetic particle detector. We have an EPD-I and an EPD-E. And these two spacecraft are spinning. So they're going to be able to look at the pitch angle distribution of the precipitating electrons, which neither of those other missions, none of the other missions I've identified so far has really been able to get at. They'll do it on sort of a spin time period, which for the first one at least is currently 24 RPM, so it's a few second spin period. They have a magnetometer as well, FGM, and they were launched 6 months ago, 8 months ago now, something like that. They've gone through a fairly long commissioning phase. Both spacecraft are now fully commissioned. Elfin A has the electron detector fully commissioned and operating some. The ion and the FGM are still in commissioning. Elfin B is spacecraft almost done, and then the science instrument will follow soon after that, I'm told. So their hope is for using the SPDF. They aren't listed currently under the CubeSats button. They have their own button, which I feel like that's kind of a mistake. We should try and all coalesce around a place to find CubeSat data. Their hope is they'll start pushing level 2 data by the end of the summer. They estimate, and I don't know what this is from, remaining mission lifetime of about 6 months. Since their data is very new, they have sort of a pose meet bed pass here, and then a nearby Elfin A pass. And you can see they have much larger energy range and much finer energy resolution. They are also seeing their spin tones as they spin. This is now the 2-second periodicity. So they are getting some sense of pitch angle information already, which I think will be exciting. You can see some breakaways from just a constant pitch angle distribution. So now an even less exhaustive tour through future CubeSats. I say this because, in part, there are many CubeSats in the pipeline, and there's no clearinghouse for all the data or for knowing how to coordinate between all these missions. So I think it's an important thing for us to think about doing. If you're operating a CubeSat and you want other people to use your data, we need to come up with a way of making it publicly available in sort of a realistic way. Colorado is coming back with a sort of an improved version of CSSWE. This is CIRVE. I never know how to pronounce their acronyms. CIRVE. Okay, it's better than CISWE. It's an improved version in acronym as well. It's a slightly modified version of Reptile, Reptile 2. And this is mostly dealing with interradiation belt, and it's done a couple of improvements, basically improved energy resolution and anti-coincidence on the instrument. So they've moved to pulse height analysis on the energy resolution and using anti-coincidence on Reptile. So they've improved the instrument, and that required a few additional changes, so they're moving to deployed solar panel arrays. Another upcoming mission is REAL, which is Robin Millen at Dartmouth, myself at Montana State, and Tom Soterelis at APL. REAL is also looking for the pitch angle distribution in precipitating electrons, but this is going to be doing it on microburst timescales, so a lot faster. It's another 3U coming in a few years. It's got sort of similar energy range, maybe expanded energy range compared to Firebird. GTO-SAT is coming up as well. This is led by Lauren Blom at Goddard. This is the first CubeSat to operate in GTO, we hope. It's got sort of an adapted version of the MagIce medium on board, as well as a magnetometer with some Maven, Juno, and Solar Probe heritage. Cupid is upcoming. This is a CUSP imaging led by Brian Walsh at BU, and this is using soft X-rays to image the cusp. So this is at least not a radiation belt instrument. So I did sneak one non-radiation belt thing in here. So that's just the summary of where you can go and find this data. Again, I do think that if there's one thing that preparing this talk made me think about is that as short missions, as limited missions, we really do need to try and conglomerate our data and make it sort of publicly available in a central story. So, thank you.
Do we have time for a quick break?
Yeah.
Perfect.
It's a great talk, John. Can you talk a little bit more about the details of the challenges in getting the data to the ground, and maybe look to the future, how we might think about that? Because if we're thinking in the community about maybe a constellation of 50 CubeSats and we can't get the data from one, what are we going to do there?
Right. I think that's probably the main issue right now. So there are big ideas out there. NSF just ran a CubeSat Ideas Lab where they were comms was probably the leading component of that, so there are people who are working on the problem. I will say, you know, Real, which is the one I'm most familiar with, we are planning on using S-band down, so we will be getting a megabit per second down, maybe 2 megabits per second down. Licensing is a huge issue for CubeSats, and it's actually headed in the wrong direction. It's looking like it's getting worse. I know aerospace has done some laser comm stuff, which is, I think, a huge potential savior to a lot of these. But I think getting the data down is definitely the biggest challenge in the CubeSat framework.
So I'm wondering if launch opportunities is also a challenge, or if that's something that, are you able to find launches that are needed?
I have never felt particularly constrained by the launch opportunities. I think the Alana program, the piggyback program has done a very good job of providing those. It's a long line to get in right now of things waiting for piggyback opportunities, but in the end, it has never been a real problem. I think going to geotransfer orbits is going to be presenting bigger issues, but I think we'll see as that develops. I mean, getting out of low Earth orbit is potentially difficult, period, and propulsion to control yourself in those sorts of orbits and deorbit appropriately and issues like that is going to also be difficult. But if you only want to go to low Earth orbit, launches have not been a problem.
Unfortunately, that's all the time for questions we have right now, but we'd like to thank our speaker again.